I'm Hariharan Devarajan. You can call me Hari. I'm a computer scientist at Lawrence Livermore. Today I'll be talking about a little bit more from the application-centric point of view. A lot of the talk is going to focus on deep learning and how data loading works there. Underneath, for us to actually do the optimizations, we use Flux a lot to manage resources. But the talk is going to mostly focus on how, from an application-centric point of view, you can do these things. All right. So I think this slide is kind of outdated from the perspective that everyone kind of knows and wants to do deep learning no matter what domain of science you're using. And the key thing here, I think, is eventually deep learning depends on a lot of data, and you cannot get rid of that. So data loading is a real problem there, where you need to give it tons of data in order to make any useful scientific predictions. I use this slide just to set the background right of how typical deep learning training works from an application perspective. Let's see if I can get a pointer here. Can you see the pointer on the screen? Yeah, okay. From an application perspective, typically you'll think about, okay, someone wants to read the data, so you write some form of for loop from a data loader and compute data on it. What essentially happens underneath on these frameworks is it will spawn some form of workers, either through processes or threads, depending upon what framework you use. And then underneath, you would use some form of POSIX or Python-based APIs to access your data. And essentially, you need to go through all these layers of asynchronous behavior. So the dotted lines here are asynchronous behaviors, and the solid lines are synchronous to the parent call. So the data loading itself in this framework typically happens asynchronous through the pipeline. So you are looking at a lot of compute and I/O happening in pipeline. I have some visualizations later on which show this. So at a high level, what's the problem? Understanding what's happening within deep learning in terms of data loading is challenging because it's very different from the pipelines that we are used to, where we have iterative workloads doing bulk synchronous I/O, versus here everything happens asynchronously. So there is a lot of notion of perceived throughput or perceived I/O that you have to deal with. And so as an effort to improve our understanding of scientific workloads using deep learning, our team has been working on building benchmark and tools that can support such workloads from a data-centric perspective. So the benchmark is called the DLIO Benchmark. Today it supports different varieties of doing data loading. You can tune your, make it emulate any different kind of frameworks, DALI data loaders, Python, PyTorch, TensorFlow. You can also add computation kernels. You can actually put your own data loader into place. So it's a very extensible kind of a benchmark. And the DFTracer is essentially data flow tracer, which basically means that it's doing performance monitoring, but from a data-centric perspective in this kind of a pipeline. So at a very high level, DLIO benchmark basically is a very componentized modular framework, which allows you to configure different kinds of deep learning workloads directly through YAML files or bash scripts, however you wanted to do it. It has these abstractions for reading. So at a high level, again, as I showed, you will have data loader at the top that you would be building. So it has abstractions for you to write your own data loaders. And then when you want to talk to different kinds of files or data samples, you can basically configure different readers. On top of that, you can also build your own computation kernels, like if you wanted to do cross-component studies of looking at how computations and I/O behave with each other, how the overlap happens. You can do that kind of stuff custom in this, and have communication pipelines as well. So essentially, it's a very pluggable design that you have there. On the tool side, the DFTracer, why do we have it? The main reason for having DFTracer was that all of the existing data-centric tools typically did not capture the dynamicity of the runtime from these frameworks, so there were a lot of missed calls. And even when they did, it is hard to correlate the low-level system data calls that were happening in context of the deep learning. So you want to understand where your I/O is happening, but in the context of the steps and the epochs that the deep learning training is doing. And that's kind of missing in the current state of the art. And that's where it comes through. So just as a figure for motivating you why we did this in the first place is we integrated a lot of existing tools like Scorpy, Darshan, Recorder, and tried to fix their issues. What ended up happening is a lot of these formats store data in such a way that you have minimum footprint while capturing, but really don't think about the analysis pipeline later on. And so as you see here in the lower side of it, as you go to 1 million events, which is very common for deep learning running for a few hours, 1 million events of I/O events, you'll start seeing the trace sizes, the time to load the data, everything keeps exponentially increasing. And so DFTracer on the last column is more of an analysis-friendly framework, which will keep the overheads low, but at the same time maintain a performance. So I promised you some visualizations. So essentially, at a high level, if you see here, what we are showing here is through DFTracer, you can capture these different layers of checkpointing from Python to C++ to the low-level system calls. You can kind of understand where your actual loading is happening and how that correlates to the asynchronous threads or processes underneath where your actual I/O happens. And also identify through tools what are the stalls. So just to give a few quick use cases, here, you can think about, so this was a workload run, the Llama model running with the Megatron and Deep Speed frameworks with a checkpointing library called SCR. So initially, when we looked at the application, essentially we were trying to optimize it. What's important here at a high level is typically you would look at how much time application spends on I/O, but what really happens underneath is there's some portion of time which is dedicated to checkpointing. And then if you really look at how overlapping happenings between compute and I/O and different pieces of checkpointing which don't overlap, you need to optimize the below layers, which will eventually optimize. So there is this layered performance monitoring that you need to do, an analysis you need to do to actually optimize it correctly. From another direction, if you look at trying to optimize deep learning workloads from the POSIX layer 2 all the way up to the training above, this is another example with the Stormer application at Argonne, where we were trying to understand what's happening from the below layers, where you're looking at, okay, overall, this is what happens on the file system. These are how data accesses are happening. This was an HDF5 data set, so there were smaller accesses which looked like data accesses, but actually are metadata for HDF5, and there were actual metadata operations. And from this, you can kind of understand at a high level how the processing is happening from the data loader level, which was the second bar, the pink thing there. And there also you need to think about, once you have the data, how are you pre-processing it? And all these eventually would contribute towards the data loading performance. So we need to look at all the lower levels, but also correlate them with all the higher levels in order to actually make sense of the data loading performance that you're getting overall. So in summary, this was a quick, brief overdone on how data loading works for deep learning. I discussed a couple of key modular design choices for DLIO and DFTracer and showed some graphs and on how you can use that for tuning deep learning workloads through these tools. Thank you. And I think we have a few minutes for questions. So use the QR code to play with these and feel free to reach out. Yeah.
Hi, thank you for the talk. So I think one of the difficulties or traditional difficulties, I don't know if this has maybe been solved in the approach that you've taken, is when you're trying to look at Python, where Python is spending its time, you can't look at lower layers, I guess, into the stack, but it seems like maybe you are able to reason about the way it's spending the I/O time, or I'm not sure, is the optimization like So within the Python layer, is it below there? And
So traditionally, there are tools which will do one or the other. So there
Right.
are enough tools which will look at the system calls and say, this is what is happening on the lower layers. There are tools like PyTorch profiling themselves give you, which will tell you what time is spent on Python. What we realized is you need both. And the reason you can't just combine them is because the way they calculate time, how they merge their timelines don't actually make any sense. And so you need to think about, from a holistic perspective, okay, I spend this much time on NumPy load, but out of that, only 10% of it was I/O. So then you have to go back and figure out, oh, NumPy load does a lot of buffering, some compressions. Should I switch it to NPY files, which use mmaps? So you need to because of those gaps in the timeline that you are seeing, you can kind of then infer how to optimize which layer, the Python layer or the below layer. And because of asynchronicity also, a lot of the tools that we're working with Python are harder to do with deep learning framework. So that's why they all went with their own, because they have their own ways of managing processes and all. But they are not very detailed in terms of data loading performance. That's where the DFTracer tool kind of comes in.